So, thank you very much to the organizers for inviting me. Thank you everybody for being here on such a nice, warm summer afternoon, evening. Past my bedtime actually. And I'm here to tell you about dust as well. And I actually thought that it was very beautiful that the name of the event is Dust to Dust. Of course, the phrase ashes to ashes, dust to dust is something that I've heard many times during my life because it's everywhere in literature and in poetry. But I actually looked it up for the first time when I was preparing this talk, and I found out that it comes from the Bible, as these things usually do. And it's a reminder of how we humans come from the earth, and when we die, our bodies are going to decompose, and we're going to be back in the earth where we come from. So it's something that's kind of meant to put you in your place. And actually what's a little bit surprising that maybe you don't know is that it doesn't only apply to humans, it actually also applies to stars, this dust to dust biblical law. Okay. So Sasha's already explained to us that the Milky Way invisible light is we can see stars, and then we can see that these stars are obscured by dust. She gave this analogy of the pizza, and she said that the interstellar medium is the mozzarella. But actually, if we do a little budget of the mass in a galaxy, the mass can be locked in compact things, so in a star, in a planet, in a black hole, or you can have gas that sort of permeates everywhere in the galaxy. And then you have dust, which are these solid little particles that are made of carbon, oxygen, iron, silicon. And then there's, of course, dark matter, but that's a topic for another sermon of the top. So there's a couple of things that I would want you to take home from this talk. One of them is that in galaxies in general, matter recycles, so it goes from one place to another. And another one is that these elements that form dust, these elements that I was saying, don't just exist in the universe, they were formed somewhere. So as we learned in the quiz, in the universe at the very beginning, during the Big Bang, hydrogen was formed, and there was also a little bit of helium, but everything else is not produced in the Big Bang and had to be formed at some point. And maybe we can go to the next slide. In order to answer the question of where dust comes from, we need to look a little bit at the life cycle of the star. So this is something that Sasha also mentioned in her talk, but we're going to go into a little bit more depth here. So stars are born in these giant molecular clouds, which are dense and they're cold. And they are composed mostly of hydrogen gas, but they also have some dust. And then at some point, these clouds of gas have instabilities, and they gravitationally collapse onto themselves. So this is a relatively slow process, but eventually you have little pockets, little inhomogeneities that cause that these clouds of gas collapse onto something like a wall of gas that then eventually at the center reaches a sufficient temperature that hydrogen can burn into helium. That is what I wanted to say about this. So, as Sasha said, at some point you have this protoplanetary disk phase of star formation where planets form, and that's because little dust grains stick to each other and actually form the seeds that form the planets. But the rest of the gas goes into the star, and the star starts its life by igniting hydrogen fusion. Okay. So when molecular clouds undergo an episode of star formation, what happens is that there's a distribution of stars that is formed of different masses, lots of small stars and a few large stars. So low-mass stars are stars like the sun. We normally say that the boundary between a low-mass star and a high-mass star is around 8 solar masses. And the sun is roughly halfway through its life, and what it's doing is that in its core, it's taking every 2 hydrogen atoms, combining them into a helium atom. That nuclear reaction releases energy, and that's why it shines. Sorry? Okay. So the sun is shining, and it's taking these 2 lighter hydrogen elements, and it's converting them into one heavier helium atom, which is also still a light element. And then eventually, the core of the sun, which is where the nuclear reactions are taking place, in order for the nuclear reactions to take place, we need to have a certain temperature, otherwise it's not happening. And that temperature can only be reached in the center of the star, in the core. And at some point the core runs out of hydrogen, so then there are other nuclear reactions that need to happen, and in this case it's helium that burns into carbon. So we're already creating carbon, which is one of the elements that Sasha told us about, that form dust. So we're kind of in the right direction over here. Now, when the star goes through this phase where it's burning helium into carbon, it actually, this will happen to us, this will happen to the sun. It's going to get much bigger and puffier. And when it gets bigger and puffier and less dense, it gets colder. And when it's colder, you have a more suitable environment for dust and molecules to form. So then you have this expanded star that has a little bit of dust and a little bit of molecules in its envelope. And then because these dust grains are bigger than individual atoms, they actually have a higher likelihood of interacting with the light from the star, with the photons from the star. And that means that when the photons hit the dust grain, they give it some momentum. And then the dust grain is slowly ejected out of the gravitational field of the star. And this is what we call a stellar wind. And it's a process by which stars lose some of their mass to these winds, and they eventually just lose. And then what happens, if we can go to the next slide, is that we have this stage of planetary nebula. At this point, the star has not only run of all hydrogen in its core, but it's also run out of helium. But there are no, the conditions are not suitable for the star to burn any heavier elements. So at this point, we just have, this is called a white dwarf. It's a dead core that's no longer producing energy, but it's still very hot. And the star is slowly losing all of the mass of its envelope, slowly shedding it out. And we have, for a brief period, we have this planetary nebula stage that we can see. Now, as I said before, this has a lot of molecules and a lot of dust, so this is one of the ways that the elements that were formed by the star during its life, when it was undergoing nuclear reactions, are enriched in interstellar medium, and the stars are also returning all of this dust to the interstellar medium. Remember that the stars were made from these clouds of gas and dust. However, here we run into a little bit of a problem, because we do know that these low-mass stars produce dust, but actually when we take observations of very distant galaxies that were observations that correspond to very early times in the universe, we already see a lot of dust. But this process of stellar evolution for low-mass stars is actually very slow. So we need something that's able to produce dust at much faster time scales than these low-mass stars can. And so our next candidate for our dust budget, for the production of dust that we need in order to explain these early universe observations, are massive stars. Now, I can't show you a nice, resolved, beautiful picture of a high-mass star in the same way that I showed you a picture of the sun. But this is a cluster of high-mass stars. This is a Hubble Space Telescope image, and the brightest one here, we believe, is around 50 solar masses, which is very, very large. And massive stars are born in clusters, and the thing with massive stars is because they have more mass, you can imagine that their core has a lot more pressure, has a lot more temperature, and it actually is able to undergo more nuclear reactions. So nuclear reactions of bigger elements. So it can actually fuse carbon into oxygen, neon, and eventually they can also produce iron. So maybe we can move on to the next slide. What happens at the end of the life of a star, once it starts burning silicon into iron, is that the star there are no nuclear reactions that can happen combining iron atoms that release energy. So it's kind of reached the end of its life. And the energy from the nuclear reactions was actually producing this pressure that was counteracting gravity. So at some point, when the star is not able to produce energy anymore, it can't support its own weight against gravity either, and it collapses. And this is what we call a supernova explosion. So actually, it's not only massive stars that undergo a supernova explosion, but all massive stars will end their lives in a supernova explosion. This one is actually a little bit cheating because this is a Loma star that exploded, a white dwarf that exploded. They can also do it if they reach a certain critical mass. But for the purposes of this talk, where we're trying to figure out where the dust came from, we know that that supernova can happen very early on in the life of the universe, and they're a good candidate for the production of dust. Okay, so maybe can we go to the next one? Maybe you remember this from the quiz just now. This is a very famous supernova remnant. This is what it looks like roughly 1,000 years after a stellar explosion. So you cannot see it in the image, but in the center here there's a neutron star. A neutron star is a very dense star made of neutrons that's very small. It's like of the order of a few kilometers, but it has the mass of the sun, a little bit more. And then everything else is just exploded material that originally formed the star. So this is the way that these elements that were locked into the star are kind of unbound and begin to be part of the interstellar medium and are available for the formation of dust. Because what did I say, that these stars can burn elements in such a way that they produce, for example, silicon, which we need for the formation of dust, iron, which we need for the formation of dust. So we have the materials there. But as Sasha also mentioned, dust grains are actually a little bit fragile. And a supernova explosion is a very violent environment. So it's actually a little bit of a hostile environment for these grains to survive. And for a few years in our field, it was actually not clear whether supernova remnants were always able to solve this problem of where dust comes from, or maybe they just destroy more dust than they create. So this is something that the community had been arguing back and forth for a while until we came up with these observations. So maybe we can go to the next slide. This is a simulation, but the star that it's simulating is an exploded star called 1987A. And 1987A for us is like the gift that keeps giving. It's this supernova explosion that happened 36 years ago, very nearby in the Large Magellanic Cloud, which is another galaxy. So nearby, you take it with a grain of salt. But it's the only supernova explosion that's local that we've been able to observe since we have these very advanced telescopes. So for us, a lot of the supernova science that we know of, and especially of the evolution of a supernova into a supernova remnant, comes from 1987. So this star had undergone an episode of mass loss due to stellar winds that high mass stars can also have. In fact, they lose a lot of their mass through winds. I should have said that before, but I didn't. But it underwent this episode of mass loss and it formed this little ring. So this is material that the star shed before it exploded. And then what happens, maybe if you can see the video, is that when we have the supernova explosion, the supernova blast wave interacts with the dust and totally destroys it. But what we're beginning to see is that actually the dust is reforming after the passage of the shock. And this was quite a surprise. I mean, that's it. It's a very short video. You can show it again if you want for effect. So that was quite a surprising result, that dust grains could reform quite so quickly after the passage of such a shock wave, because especially at very early times, these shocks are moving at thousands of kilometers a second, so you can imagine that they just destroy everything they encounter. Okay, so we can maybe move to the next slide. This is the end of the talk. So what I want the take-home point to be is that you can think of our galaxy a little bit like an ecosystem, where matter moves from one phase to another, and sometimes it's in a bound object, sometimes it's part of the interstellar medium, and it's thanks to that process that we actually exist. So the atoms that form us are synthesized in stars, and apparently many of the atoms come from the Big Bang, but in mass we definitely come from stars. And you know, our planet exists because these dust grains were there for our planetary system to form. So like this phrase of dust to dust, it doesn't just mean that we're of the earth and we'll go back to the earth. It actually also means that we're of the universe and we'll go back to the universe. So thank you for listening.
Questions for Miriam?
It's interesting to see the reformation of dust grains. So what's the time scale that dust grain can reform from, the destruction?
I will send you the paper, Monica.
Thank you.
I would say, this is 87A, so I think the ring was shocked recently-ish, and the dust grain reformed even more recently, so maybe like a time scale of decades. But I will send you the reference.
Maybe I can kind of ask a similar question. You talked about low mass stars and high mass stars. What are the time kind of scales of getting to a supernova stage between low mass and high mass?
So for a high mass star, the time scale varies depending on the initial mass of the star, but it's roughly of the orders of millions of years, tens of millions of years. And for low mass stars, there's a very big diversity actually, because you first need to get to the white dwarf stage. So the star needs to slowly burn its fuel, and then it has to lose its envelope, and then you need to achieve this critical mass that I was talking about. That's the Chandrasekhar mass that can trigger a thermonuclear explosion in a white dwarf. So that very much depends on the distance of the companion, the accretion rate, and all these things. So very many years.
The questions?
A bit of a different question, but one, do you have dust yourself? I once saw a documentary of people looking dust in the United States, so I wonder where can you find dust in Europe, maybe in the Netherlands, if you happen to know?
Sorry?
So I saw actually people once in a documentary looking for space dust.
Okay.
And
Under my head, no. I have no idea. That's a question for Sasha, I think. Where would you find dust in the Netherlands?
In the Netherlands, from outer space. Could you?
I don't think you can. Yeah.
probably not then. And in Europe, is it known?
I think from what I understand, you can have fragments of dust that come in meteorites, but I also don't know how they survive the passage through the Earth's atmosphere. I imagine that they're very disturbed after that. I don't know, Sasha, do you want to answer that question?
Looking for meteorites in the Netherlands is a terrible business because,
So yeah, there's dust. If you want to find it in the Netherlands, here, and it comes from it has to be coming from outer space. Your best bet is a meteorite, I would say. But looking for it in the Netherlands is terrible because it usually lands in water. And I tried to find one with a whole group of people once that had to be somewhere in the field. A fragment of it was already found. We spent hours and hours trying to plow through the fields, but no way. It's a few years ago, I think 5-6 years ago, when this fragment was found. And it was actually quite pristine material, so perhaps some instant dust particles in there. But yeah, other than that, it's very difficult.
maybe at the back. Go ahead.
Me?
Yeah.
Okay, cool. Is there any other samples of like supernovae that you could study for the release of the dust, of like interstellar dust? Because you gave an example, a very cool simulation, visualization of that one supernovae explosion releasing dust. And could you correlate this model to other samples?
Yeah, there are other supernova explosions that you could do something like this for, but it's just very dramatic in the case of 1987A. But whenever a source is relatively young, so it's like only in the few hundreds of years, then you can see these sources have dust. So a very famous source is Cassiopeia A. It's a very well studied supernova remnant, and there people have observed dust. The problem is that people have observed dust there in a part of the supernova remnant that has yet to be shocked by the reverse shock. So it's unclear whether it will survive the encounter with the shock, and after that, how long it will take for this dust to reform.
Yeah, so you mentioned that silicon burns to iron, and then the star collapses because iron takes more energy to fuse. But as the star collapses, is it possible that more elements are fused with that extra energy as the star collapses? Or is the time scale too short for higher mass elements?
Oh,
to fuse? Like,
if they use the gravitational energy?
Yeah, it's like at the end of a life, you know, because it stops at iron and then it's collapsing. Are there higher mass elements formed in that kind of moment, and maybe on a small scale?
Yeah, so that's actually a very valid question, right? If stars stop fusing elements at iron, then how can we see massive elements that have a higher mass than iron? And you're indeed right that it has to do with all the energy available during an explosion. We call this explosive nucleosynthesis, and the type of elements that are produced are different for type 1a supernovae or for collapsed supernovae. And a lot of it has to do not just with the energy of the infalling material, but also that a lot of this material happens to be neutron-rich. So it's quite complicated nuclear physics that goes on, but yes, indeed, other elements do form at the stage of the supernova explosion. Basically, every element that has an atomic number higher than iron needs to have this type of events to form.
I guess when the supernova explodes, most of the reaction is helium and hydrogen when they're out of the shell. And only a very small portion is actually the heavier elements of the fire. Or is it mostly actually the heavier elements that are the heavier?
So you're right that there's a lot of hydrogen, for example, that never makes it to be fused, and a lot of helium that never makes it to be fused. Actually, it's relatively common for massive stars to lose their hydrogen envelope and sometimes also their helium envelope due to these stellar winds that I was talking about. So sometimes when they explode, they just even have no hydrogen. We call those type 2 supernovae or type 1 supernova, where we don't see any hydrogen lines in the spectrum. But how much mass they produce of the different elements, I think that depends very much on the size of the supernova to begin with. But yeah, like definitely not 100% of the mass of the star is metals. It's something other than hydrogen and helium. There's still a significant amount of hydrogen and helium that's not burned because it's in these outer layers.
Type 1 supernova are quite close.
Yeah, so that's a little bit of an anachronism. Yeah. Yeah, so this is one of these things about astronomy that things are named one thing because of historical reasons, and then like when we actually think about the astrophysics, we'd be like, okay, that's a terrible name. Type 1 means no hydrogen lines in the spectrum. Type 2 means hydrogen lines in the spectrum. Type 1a are type 1a so white dwarfs exploding, and they're like a totally different category. And then there's type 1b, type 1c, and those are core collapse supernovae in the sense of like a massive star that collapses because it can no longer counter gravity. So it's just a bad name. So it's actually type 1a and core collapse.
I thought that was type 2. It's type 2.
Yeah, no, so type 2 are core collapse. Type 2, type 1b, and type 1c jointly are core collapse. And type 1a are the only ones that are white dwarfs exploding. It makes, yeah. It's a stupid name, but that's the way that we call it. Because it made a lot of sense back in the day when people were observing the spectra of supernova, like, oh, these don't have hydrogen lines, these will have hydrogen lines. And the reason that type 1b and type 1c don't have hydrogen lines is because they've blown away their hydrogen envelope through winds. So by the time that they explode, they just don't have any hydrogen.
So like a pure silicon and carbon atoms.
Well, and the other, like carbon, oxygen, neon, yeah. Oh my god, yeah?
So if we find dust in very early galaxies or very old stars, like the 12 billion year one I think was mentioned. Are we saying that like it can't have happened during like the Big Bang because of the elements that we found in space dust?
No, because the Big Bang is just, I mean, the conditions in the Big Bang are just unparalleled in the rest of the universe. The temperature, pressure, density, like they're just totally different from what we see even in the very early universe. So the only elements that were able to form during the Big Bang were actually hydrogen and helium, and then very few amounts of lithium and other like elements. But basically, with that's also a very important process of nucleosynthesis. We call it Big Bang nucleosynthesis. And there it was a little bit of a race between the fact that these reactions needed high temperatures, but also the universe was expanding and therefore getting colder. So it kind of only had enough time to get to a certain amount of hydrogen and helium before everything was too cold for nuclear reactions to take place.
Any final question? Okay, thanks.
It's not a question about the talk, but of the quiz that happened before. So I think there was a question about which of these do not contain an element from supernova remnant. And I think Atacama Desert was not in the answer, but I mean, in the end, all elements were synthesized in the core of stars and dispersed into supernovae. So
yes, so that's actually a thing of the quiz. But I think what they mean more is like what are traces that we can see in ice or in rocks that we can unambiguously trace back to particular supernova events. And I'm actually not sure how they do this, but I guess they measure isotope ratios or something, and they figure out that like, okay, these ratios tell us that this is an element that arrived however many hundreds of years ago when we saw that supernova explosion happen.
Okay, let's thank Maria again.